So, welcome to the Friday afternoon physics colloquium. So we're very honored to have Dr. David Rakestraw from Lawrence Livermore National Lab. This is going to be, hopefully, an interactive colloquium. And actually that depends on the helpers, which are me, Dan, Roger, Pete, Michael, and I already said Dan.
Chance.
Oh, Chance. Where's Chance? Oh, and Chance. Okay. So anyway, it's going to be interactive, we hope. And again,
You guys are on. You're on your bill.
All right, and so Dr. Rakestraw began his career at Ohio Northern University, did his PhD at Stanford, actually in chemical physics, which actually, if you know about chemical physics, is actually essentially physics. And then he went to various national labs, so Sandia, Lawrence Livermore, and somewhere in there he ran a multi-million-dollar company. And so if you want to know more, you can ask him like during the Q&A session. But let's go ahead and let Dr. Rakestraw get started. Welcome.
Thank you. Happy to be here. You know, I'm going to talk to you not about the research that I've done for decades in the science labs, but about something that's been my passion for just the last couple of years. And I've been working in this area of STEM education. And it came from when about 4 years ago, I was frustrated with my kids who were going through high school, and kind of the teacher kind of differentials that were there in high school, and that students were being forced to choose their college majors based on their high school education, when oftentimes their teachers were not particularly good in a particular subject, and that was affecting, you know, major decisions that they were making. And so I whined about it for a while, and then I decided that whining wasn't going to help, so I decided I would try to help. And so I went part-time for a year, and I taught in high school. And from that experience, I learned something about using phones to make measurements, and I got very excited about it. And I really believe that this is going to have some dramatic effects on how we can educate scientists and engineers. And so what I want to do is I want to share that with you guys today and talk about it, okay? And so, so today what we're going to do is we're going to talk a little bit about what those capabilities are, but then we're going to basically spend time doing stuff, okay? So for the most of this time, you know, you guys are going to be actively involved. You're going to be you can stand up, you can roam around, you can walk. You're going to be doing, you're going to be participating in this. So no sitting back, just watching, listening. If you thought you were coming here for a nap, you know, it's not going to happen. We're going to get you involved, okay? And then at the end, okay, we have your fellow students and teachers who are going to lead some special sessions where you're going to get to focus on something a little bit more detailed, where you're going to use something more than your phone to help assist in doing some experiments. Okay? So that's the plan for today. So these phones that you guys have and that everybody carries in your pockets, okay? I mean, they are absolutely remarkable. They have technology that's been driven by hundreds of billions of dollars a year in investment. Okay? I mean, hundreds of billions a year, you know, driving the technology that's in your phones that you're carrying around with you. I mean, the power in them is so amazing. Okay? And the fact is, you know, they can be used for a lot of different stuff for, you know, that the manufacturers have kind of figured out over time. So they have these 3-axis accelerometer. It's got a 3-axis gyroscope, a 3-axis magnetometer, a pressure transducer. These are all these kind of microelectromechanical devices, right? So they're these kind of combination of electronics and microfabricated systems that allow us to make these measurements, and we'll talk about them. You got microphones, you got GPS systems, you have these amazing CMOS cameras. I mean, when I first started my first job at Lawrence Livermore National Lab, I bought an astronomy camera to do some nonlinear spectroscopy with, and I paid $80,000 for a camera that was like I think it was like 512 by 512, okay, pixels on it. It was a CCD camera, and it was like 80 grand, okay, to get this astronomy quality kind of camera, right? So now you have cameras that are, cost $1, okay, that are made out of CMOS, and they're, 4,000 by 4,000, and they're, so much better than the camera I bought for 80 grand, back in, the early 90s. So it's just remarkable advances. So it's got computing power, it's got these high resolution graphical interface, it's enabled with Bluetooth and Wi-Fi, it leverages this huge amount of infrastructure, the satellites, the cell stations. I mean, it's remarkable, right? And it's got every student in the country is an expert user of the device, right? We don't have to teach any of you guys how to use your phone, or any other kid in high school or middle school for that matter, right? Because you all can just pile in and do it. So, so this thing enables what I would say are some remarkable things in related education. I'm not going to take a lot of time to go through all this, but the ability to do super precise measurements that most physics, most of the equipment you have in physics classes and things you did. So my daughter goes to Duke and my son goes to Occidental. They're about 75 to 80 grand a year. And their physics experiments can't match anywhere close to what they can do with their phones, okay? At these, expensive universities that are, I'm just appalled at what they end up having to do. But these measurements these tools are so powerful, and they enable, every student to be able to do stuff both inside and outside of classes. You can change the dynamic of how experiments are done, okay? It really changes how you think about experimental science and what you can assign. You don't have to send somebody out to do a homework assignment. Send them out to go make a measurement, on the world on something, right? Have them look at the data, figure it out, the things that they actually collect. And they're going to collect remarkable data, okay, because these sensors are so good, okay? So it really offers this opportunity that I think could change things. And I don't know whether any of you guys came from areas where maybe your school wasn't so, didn't have resources, wasn't able to do things. Every single kid, okay, in the country, just about, okay, has a phone, or his friend does, okay? I mean, I think it's like 97% of high school kids in America own smartphones today, okay? So this is not something that, this is something that can be done by everyone. Okay, so there are a couple different kinds of applications that people can do for your phones. Okay, some that allow you to get to a whole bunch of those sensors simultaneously. Some that are specialized that use kind of one of the sensors, right? And we're going to use a couple of those today. Okay, so what I want you to do is get out your phones. Okay. You're going to download this app called Fiverr. So if you haven't already done it, download that app. And if you don't have phones, can't download an app, I have a bunch of phones up here with the apps already downloaded. So,
Dave, you want me to pass those around?
Yeah. So anybody who needs a phone can grab one of these. What I found before is I spent all this time getting these phones and going through all this paperwork at the lab to have these phones that I can give to people. And then nobody wants them because they all have their own phones and they don't need them. So we'll see whether that, how many of you, and this is the code that you use to open your phone.
Okay, looks like everyone's got
These
one.
phones to keep?
No? No, you don't get
So, open up Firefox.
So, is that code only for what?
That code is to open up the phone.
That's for the phone you're using.
Yeah, so if anybody's using the phones I'm handing out, they have codes so that you can use them.
Okay.
So on all sensors, acoustic.
So you see all these different things
Oh,
here.
no, I'm good, man.
Okay.
You can see.
So you're going to start using it. Okay. So the first thing I want you to do is select acceleration without G. Okay. See, hardly anybody needed them, right?
Yes, nobody.
Okay. So I want you to put your little bench up, okay, in front of you. Okay. Set your phone on it. Okay. Then I want you to start data collection. Knock on your table a couple times, and then hit pause. You should get something that looks a little bit like this. So your phone will be collecting the data. You'll see it. Okay, so everybody should have collected a little short period of data and have it stop. Okay,
That is.
and so everybody not able to do that.
That's what they are, the three different
Anybody need
parts.
assistance?
So you get three-dimensional.
We have helpers in the room to help you. So you guys that are the helpers, you guys maybe you can kind of stand up and roam around, and if you see anybody having trouble, you can give them help. Okay? So now that you have it, I want you to tap on one of the tabs and rotate your
I
phone.
need help immediately. out of the way.
So just anyone?
Yeah, tap on any of the graphs that you want to look at in more detail. Okay? Rotate your phone. You should see it kind of blow up. You can see it on the screen like this.
Well, I guess make sure to set the phone to be maybe auto rotate, for example.
Yes. So then what you can do is you can, if you see this pan and zoom, so you can use your fingers to actually pinch and do it. Don, do you need one?
No, I'm watching, but I'm going around and checking it out.
No. You gotta.
No, man, Don. Yeah, Don.
Come on, Don.
You guys know Don. He don't even know one of those. I'm good. I can observe.
You sure?
Yeah, I'm good. I'm going to watch here, right? You said I could walk around, didn't you?
Yes,
I got my
absolutely.
mask on, I'm going to walk
Okay,
around.
so you can pinch and zoom, and you can kind of zoom in on your data and look at the details, right? Okay. The other thing you can do is if you go to that, you go to this next button in the middle, the pick and zoom, the pick data. You can actually tap on your screen, and you can read data points right off your screen, right? So if you want to read a value off of your screen, you can tap there, and you can read what the value is. Okay. Yes, sir.
Why is there no errors?
No errors?
Yes.
Oh, no error bars?
Error bars.
So what you can do, and I'm actually doing a really interesting experiment right now, is collecting data with this that allows you to collect lots of data simultaneously, and you can look at random noise, and you can get beautiful Gaussian distribution curves of the normal distribution of noise that you can measure yourself and analyze yourself and look at it. So you can, so that's something you can investigate and look at in detail. So it doesn't give it to you directly, but you can actually do that measurement. Yes, sir.
Seems like from the sensitivity of this thing, the error bars would be so tiny, you wouldn't even be able to see them anyway.
So we can measure those error bars, and we can try to understand. You know, you can have the students understand what's resulting in those error bars. How does it actually work? And that'll be different on different sensors. And you guys will also see different phones will have different data collection rates. Okay? So if you want, you can go to this more tools down at the bottom. You can reset zoom and it'll go back to like your original data. So these are just a couple of the different tools. If you go back to that main menu, you can see that there's like graph, absolute, multi, and simple. So there's opportunities to have different looks at your data. Yes, sir.
You know, what I'm seeing of this so far, Dave, I think this is fantastic, is they can go home and play the hell out of this. I mean, they can try all kinds of stuff, right? They can say, let me try this, let me try that.
Exactly. The goal at the end of the seminar is that everybody is going home and showing all their friends the cool things that they learned in the seminar.
I see the students going home and trying it with their phone and different stuff.
You know, what I was hoping those students is that, you know, you would have seen similar enthusiasm out of all of your professors, you know, participating actively in the experimentation.
Hey, look at him.
Oh, one could export data.
So you can export data. So this is a great feature. So now that you collected this data, you can export it. You can send it through email, text message. You can airdrop it. So, and then you can put it in your favorite, analysis software, right? So, yes, sir.
So you're the one who worked on developing this app?
So I'm not developing the app. What I'm going to show you is all the kind of things we can do with this app, the kinds of physics experiments we do. So there's a group in Germany that actually developed this app. And this is just one of them. There's many different apps, but I really like the one that these guys in Germany developed. So I use it. Right, yeah, and that was what, it's not what happens is some people say, oh, these phones, they got these things, they'll look at something like that and they'll say, oh, this isn't very useful. And that was what I did initially, and then when I found these guys out, I said, these guys did it right. These guys really have a tremendous amount of features in it. I think there's one I did, I think I cut it out of here. You can actually, if you see this enable remote access, that actually gives you a URL, okay? And then Roger can type it in on his iPad here, and you can run around the room with your phone, and he can be measuring
What do you guys
the
think so
data
far?
that you're collecting,
You can understand it?
with your
Pretty
phone
simple.
on his iPad
Yeah.
and see the data in real time. Or what I do is I put it on my drone, and I fly the drone around, and you can measure stuff. Yes, sir.
Where's the X and Y and Z axis?
So we're going to get to that in just a moment. You're going to figure that out. Okay. So, so you can, if you want to start over, you just hit that trash can, you hit clear, and then you can start up a new experiment. Okay? So, we're going to do acceleration. Yes?
So how sensitive do these get? Like, what are like kind of the scale of like the lowest vibrations that it could sense?
So, you can measure somewhere on the order of 0.005, I think, meters per second squared.
Jesus.
I mean, it's really sensitive. So I'll show you an example in a minute, because I have a bad heart, and I'm going to show you how I can diagnose my heart in great detail using this phone by just measuring the vibrations of my chest.
I mean, just really the last 10 years.
So here's what you guys got to do. So you've been playing with it. See if you can figure out what the X, Y, and Z axes are. And you stand up, move around.
That's a good
Look
point.
at talk to your friends about it.
But you got to see the orientation.
See if you guys can figure out which axis is which. So you might want to move it kind of quickly, across a couple different axes, and see what you think is the X, Y, and Z axes on your phone. Okay?
I don't
See what you guys think.
I can't even see him, John. I got a laptop. I can't even see him. You know what I kept thinking about to do soon?
Okay,
It's
I got
like
it.
you just touch something and it's right here, the whole thing.
Yeah, that's
Oh, where you can make it as big as you want it. You can just be right here. Yeah, but I can't even see them.
It's kind of funny watching people like shake their phones. Like,
That idea of hard light.
So anybody agree with my picture on the
oh,
there?
yeah.
Now, Dave, can you reset your axes? I mean, if you decide you want to put your x-axis here, or?
Not that I'm aware of.
Okay.
So the phone, so you'll have a whole bunch of different apps on here, and you'll be able to do it. Oh, he just did that would have been nice to also measure with the gyroscope. Right? 'Cause you could have-
Sure enough, I just measured the acceleration of gravity.
All right.
And it came down.
Yeah.
Free fall for a second.
You measured it. It showed you the 9.8.
Yeah, it should measure. There you go. That
Yeah,
gives
you'll
you-
see that with free fall. Exactly.
There you go.
Yeah.
It should work. You
So-
just got to catch it.
So here's how this thing works, okay? And this gets to your measurement of gravity. What it is it's basically a mass, okay, on these little spring tethers, okay? So it's a microfabricated, device in
It's
silicon.
in your phone.
It's got this little mass block, and it's on these little springs, basically, little wires that can move back and forth. And so when you move your phone, that mass in the center, Okay, do I have this laser pointing?
That image on the right, you realize how small
So
it is?
you have this mass in the center that has inertia, okay? And so when you try to move it one way, right, it basically has a resistance to motion. And when it does, okay, these little arms, okay, they're basically measuring the capacitance between these two locations, right?
What's the inertia?
Right? And so what happens is when this moves, it changes that distance, changes the capacitance, and that's read out as an acceleration. So they calibrate this to acceleration.
Are you
And
looking
then
for
there's one of
rotation
those
right
on
now?
all
Just
three
tell the
axes.
rotation?
And so that's how this thing works, okay? This was driven initially, this technology was driven initially by the desire to have sensors for firing off airbags in cars. And so they wanted to be able to see the very rapid acceleration that happened when you had an impact, okay? And that, but not when you hit a bump in the road or a pothole, right? And so it had to measure the appropriate acceleration along the right axes to be able to fire off the airbag. And so that drove a lot of the early development of this technology. That was one of the big first applications. But now, if you guys ever have fitness apps and you walk and you do stepper, you get steps. Well, you know how it's measuring steps? It's measuring the acceleration, that takes place every time you move and your phone's in your pocket, and it measures that motion. And it has algorithms that figure that out. So the guys at Fitbit, who basically developed, have you guys ever heard of Fitbit? I have one. I'm wearing one. So when they put one of these accelerometers in the Fitbit to kind of do that. We're one of the first to the market. They went IPO, made $4 billion on their IPO from this nice little physics tool, right? Yes, sir.
So actually, when I was doing what Fred did, I was throwing it up, and it went suddenly. It was only displaying one axis of acceleration, and there was a big part of it that was redded out. So is there too big an acceleration for this thing?
It has a maximum acceleration, but I'm pretty sure you didn't reach it.
Yeah.
So it should go up to, most of these phones go up to 78 meters per second squared.
Yeah, no.
Okay, because it's
Doug, are you talking about the red line?
Yeah.
That's when you pause it.
Oh, okay.
Is there a terminal speed?
Thank you, Michael.
Terminal speed, not that I know of.
Actually, they're right, Doug.
All right, you can see it.
So one of the experiments I love doing with kids is I do this experiment, and this is a really cool experiment. So I hold this guy with a rubber band, and then I let it go like that. Is that exciting experiment?
Oh my gosh, I almost, geez.
Oh,
Hey, yeah.
No, it's a rubber band, and I'm giving you all
Man,
some
that was
rubber bands.
exciting, wasn't it, guys?
Okay, so you'll be able to do this.
Look at this, I want to see it again.
But this is the interesting data. So this data right here, okay, is the data that comes from that experiment. Okay? And what you can see, and I'm not going to go into detail on this, but this part right here, so this is when the rubber band accelerates it. Okay? Then the elastomer is basically going back towards equilibrium. It reaches its equilibrium position here, so it's no longer applying a force. So the only force on the phone then is the force due to kinetic friction. Okay? So it's got a constant force of friction on it.
Yeah.
And basically, so this is Newton's second law, and it basically maintains the same acceleration right up until the time that it stops. Okay? And from that measurement of acceleration, you can determine the force from kinetic friction and the coefficient of friction from that. And you can study that for a whole bunch of different materials from this very simple experiment that allows students to really look at free body diagrams, understand the details of the process, and they collect their own data, and it's just absolutely beautiful experiment. Yes, sir.
I think one idea would be to measure and look at the data that when you flip your phone, it will change the axis of rotation because of the symmetry, and also we can try to figure it out. Could it work?
Yeah, I mean, so that's how. So I don't know. Do you like astronomy? You know?
Sure.
So
We like
the apps
everything.
on your phone is by,
Oh,
but it sense the orientation. Do you ever use like the Skyview app?
Oh,
to
yeah,
look at
that's
the stars?
awesome. That's awesome.
Well, it's using both the magnetic field, oh, he's got it, okay?
Yep.
It's
Yeah, of
using
course.
both the magnetic field and the accelerometers to actually know what the orientation of the phone is, what direction you're pointing at it relative to the Earth's orbit, or your position on the Earth. And those are how it's actually defining your position to be able to show you where the stars are in space. Yes, sir.
How good are students at being able to take that result and be able to deduce what's causing each of those sections of the plot?
Exactly. Can they read the graph? Is that what
Yeah.
you're saying, John? Can they
So-
actually read
Yeah, I
the
mean, that
graph?
seems to be like the critical thinking.
I think it's very critical, Dave.
It is
I
critical
totally agree
thinking.
with that.
And they do that, and so so it's a simple experiment, but then they start going through and saying, okay, I'm starting off, and I usually take a long time to go through this method, right? You start off and you have this potential energy that's elastic potential energy. You release that energy, and now you draw a free body diagram, you still have you overcome initially the kinetic, or the static friction to get it started, but then you have the two forces that are operating, but the elastic force is much greater than the force from kinetic friction. And then eventually, over this course of time, okay, the elastomer moves back towards its original position. At this point, at this point right here, the acceleration goes through zero. So at that point, what's the relationship between the elastic force and the force from kinetic friction? They're equal, right? Because it's essentially got no acceleration at that particular point. That's where it actually reaches its maximum velocity. Okay? And you can calculate, and I'll show you in a second. This is an example of an elevator. So this is basically measuring the acceleration on an elevator. Okay, so you can see the acceleration when they start going up, and then it basically goes at constant velocity for a long time, and then it stops. Okay, and part of the reason I want to show you this is because you got this acceleration data, you can calculate the velocity because you know the time, and so for every single measurement, you can incrementally show how much increase in velocity you get by knowing the acceleration and the time period. And then once you calculate, and so you can calculate the velocity. So the velocity you calculate, you get up to this constant speed. You know what the speed of your elevator is from that. And then you slow down. And the cool thing is, it comes down to exactly zero again. So this data is so friggin' good, right? You can integrate every single point on there. Would you think this is noise? Okay? And maybe a little bit of it is random noise, but it is random and there's a lot of data points, so it evens out. But in general, it's measuring these things exceptionally precisely. And you're measuring them, and so if you integrate that whole thing up, you started at zero, you end at zero, and you can teach them wonderful math, and then you can basically calculate from the velocity, you can calculate the distance, and you can determine exactly how far you went on your elevator ride. Yes, sir.
That noise in that middle section is a noise, that signal from the mechanism that, from the gears that pull the little steel cable.
Yeah, and it could be actually, some of it could be real.
If you want to have an idea of how much noise there is, look at the parts where you're accelerating or you're decelerating. Notice those are very smooth curves, very little randomness in that.
Yeah, so there are lots of details that they can investigate. Yes?
Just an analogy, it seems like air crash investigations, the charts are very much like this, right? You get the black box and you pull it out, you gotta determine what was happening with the airplane in the sky, and you get these kind of graphs. I don't know what they actually look like, but it seems like there's something
Yeah, I
similar.
mean, you can, and I've met, you can do some really interesting things measuring acceleration on the aircraft. You can also, as we'll see, measure things like pressure on the aircraft as well, which is really cool. So what if you can do this at home? We're not going to take time to do this one, but if you put your phone on your chest and you start the accelerometer, okay, this is what it looks like. So this is my heart rate. okay? And so I started doing this, and I was really intrigued by it. I thought it was really cool, started looking at it. And then one day, this just shows you the reproducibility, so you can see from beat to beat. So all of those all that structure, I mean, it's not noise, right? These are all these little features are real things taking place in the body, right? So I think, you know, if you're interested in life sciences and you're teaching physics for life sciences, this is an awesome, you know, investigation for them to do. But one day, all of a sudden, mine looked like this. Oh. Okay, and it continued to look like that, and I'd never had that before. And so I went to the emergency room and I told the nurse that I thought I had AFib, and she goes, well, how did you diagnose yourself with AFib? And I said, well, I measured it with my phone. She thought I was crazy. And then she got the EKG out, and she said, oh, you got AFib, and they got me into the emergency room. And the doctor came over, and I was showing him, here's what my heart used to look like, here's what it looks like right now. And he like looked at it and he started studying it. And then he goes, wait a second. He went over and got a bunch of other doctors, and they all came over and they started looking at the and they said, oh, let's watch this, right? So they started to they were watching it while they were putting this drug in me to basically put my heart back to sinus rhythm, and all of a sudden they saw it switch. You know, transition from one to the other. So they all were downloading the app and they but these things you can see are specifically related to different things. So I labeled a few up here. So this is like the mitral valve closure, the aortic valve opening, kind of peak systolic flow. You can see that when the valves close. And so there's all sorts of really interesting information. The timing between them tell you things about, you know, are your arteries clogged, what your blood pressure is, is your heart functioning like it's supposed to. So there's a tremendous amount of really interesting, you know, things that people can investigate.
You check it every day now, Dave? You check it every day?
I freaking do. I do. I'm always sitting there and I like measure it and I look at it.
Yeah, I bet.
You know, convince myself I'm okay, all my drugs are working like they're supposed to. Okay, so gyroscope. Get your phones out and choose the gyroscope. Okay, and now work on rotating your phone. So instead of accelerating it, you're going to spin it around an axis, right? So you can, you know, figure out how you want to do it, kind of move it up and down. See if you can figure out, you know, and what you should see, right, is that the angular acceleration that you're measuring, okay, will depend on the direction in which you're moving the phone, right? So counterclockwise or clockwise will give you different values. Yes, sir.
So say if someone just decides to put the axis of the phone, like if you have 4 or 5 degrees from the X direction, 4 or 5 from the 1, and 4 or 5 from the 0, you get the one type of angle. If you did just in the XY plane, then you see your actual rotation.
And you can by doing that, students can start to see how projections if these are all vector quantities, and how they project along each of the axes. They're always going to measure. So if you're at an angle, it'll measure whatever the projection of that rotation is around the axis at that particular angle.
I haven't heard any phone hit the ground yet.
So there's so what you should be able to see is the same. It's got the same axes, right? And you should be able to demonstrate the right-hand rule, okay, for the sign convention that we use for angular velocities. You can convince yourself of this at your leisure. Okay, so here's what I want you to do though. I want you to stand up with your phones, okay? And I want you to try to spin around relatively quickly and see if you can measure, you know, some constant amount of rotational angle.
Should we all do it so the camera can see?
if you go around at a constant velocity, right, you'll be able to see the kind of stay at a constant value for some period of time. So when I do this with high school classes, they love it, right? Because they want to see how fast they can spin. Okay? And then what they do is they actually count it and measure it themselves. Okay? What they, by visually looking at it, and then they convince themselves, by doing a simple calculation, that their observation of spins per second is equivalent to their angular velocities. Okay? So if you want a really cool experiment, you can prove that the centripetal acceleration is proportional to, or equals the square of the angular velocity times the radius. Okay? And so here's that data for a salad spinner. So I put my phone in the salad spinner and spun the salad spinner. And basically, I collected this data. Okay? So if then you plot the centripetal acceleration against the square of the angular velocity, you basically get this absolutely gorgeous, relationship. And I could tell in the slope, okay, when I did that, tells you exactly how far my sensor was 8.2 centimeters away from the center line of the salad spinner. So if you get with your body and you spin like this, you'll be able to calculate from if you did this experiment, you'd be able to calculate how far you're holding your phone from the center of your body. So if you did this carefully, for example, you could actually find out by putting your phone in two different orientations, you can figure out where the sensor is in your phone. Yes, sir.
So I think we addressed this a little while. We were talking about errors and error bars, guys. These things are so precise now, there's virtually no error. I mean, look at that graph. I mean, that's just absolutely gorgeous. So I mean, right off the bat, they're using such a beautiful tool now that it's taking absolutely beautiful readings and what do you got, Fred?
Another way to look at it is if the error bars are smaller than the line you're using to plot the graph, why bother putting them?
There you go. That's really what's happening. I know.
So this is really cool. So one of the things I did is if you put this, put your phone on, like in your car, and you take a drive, okay, you can actually map out your path because every time you take a 90-degree turn, you'll get some change in angular velocity, and if you integrate that up, you'll know exactly how far you turned and in what direction, right or left. And you go on a cloverleaf on a freeway, right, and you'll get 270, as you go around it. So it's really it's really quite a fun thing to do. There's just a lot of investigation you can do. Okay. Next, magnetometer. So the magnetic field. So everybody stand up, select your magnetometer. Okay. You're going to slowly rotate around in a circle twice. Okay. Tell me what you see.
Yours?
Okay.
And if you hold it flat, so it's kind of in the plane of the earth, okay, your z-axis won't change. Okay? If you held it at an angle, you'll also see some projection of the changing magnetic field on the other axis.
See some sinusoidal data.
You see some sinusoidal data. What do you think that's from? Mr. Theoretical Physicist going to University of Texas.
That's got to put them on the spot.
It comes from that the way it comes from the way like the time it comes from like it comes from the way like solutions to Maxwell's equations would work, and where you would get, we put in, you have to do wall times for electromagnetic wave solutions, you would get like some sort of equation, you would get like sines, cosines, and magnetic field, you would get electromagnetic field, you would get like imaginary exponentials, and this, you take the real part and the imaginary part, you get either sines or cosines, and it seems like there's some sort of like alternating currency nickel going with.
That's an interesting explanation. Another one might be,
You're seeing the Earth's magnetic field.
you're seeing the Earth's magnetic field.
One thing that this is particularly good at is encouraging kids the first time they see this, they see lots of error. They see, shape. The point is to get them to do this a second time, and this time more carefully, and the results are much better.
Yeah.
The second time I did this, I tried to hold the phone at the same level, and therefore the third plot, not magnetometer Z. It's a very small variation.
Yeah.
It goes from 30 to minus 30 to minus 35 microtesla. The others have amplitudes of 3 microtesla.
Exactly. So, and if you do this carefully, then what you'll find eventually is, if I want to do it really carefully, I move where there's no external magnetic fields, and I see a very symmetric shape. Okay, I figure out how do I maybe rotate it in a very smooth way. So what I did is, so you're like a, could be like what do they call this? Straight man for this. So if you put it on something like Lazy Susan or a record player or a bench, and you spin it and you're away from magnetic fields, you can get super precise measurements. You can go to the NOAA site where it tells you what the magnetic field is and what the inclination angle is. The inclination angle is the direction that the magnetic field is going into the Earth. And you can calculate those directly from this data, and it's spot on. Okay, and so you can get really beautiful data that looks like that from the measurement and get absolutely beautiful.
So to get the inclination, you just take Lazy Susan, just kind of tip it over until you get a maximum straight.
No, because you're measuring the z-axis. Okay, on one of the axes, right? So I got my z-axis, which is in this case about minus 40. And then the maximum along the horizontal axis is like 23. So I basically got 23 and 40. I can't do it, with my arms, right?
But you could do that. I mean,
yeah. And so you have that. Yeah, you can do it that way too. You could just, but this way you actually have those vectors. You just add them up. Right, so you just you can determine it. But that way, I guess you could do it. You could try to find it that way as well, to find the maximum absolute. Right. Okay, so here is this is something that we're not going to do. You could try it out on the magnetic field thing. So here's a magnet kind of going by the magnetometer. So the magnetometer is at the top of the phone. And this kind of shows you the magnetic field. And so, a lot of times you teach magnetic fields and they're kind of, they're drawing all these lines and they're kind of hard to understand and nobody remembers it and exactly what they mean and what direction they're going. Well, this is a beautiful way of actually scanning out the field with very high precision around a magnet. And so you can see exactly the directions. And so figure out later, wow, that had this kind of like derivative function. Why is that? Right? It's because when you're scanning by the top of the magnetic field's doing this, right? So when it's on this side, the field lines are going through the sensor this way. In the middle, it goes through 0, and when it's on this side, the magnetic field lines are going through that way along one of the axes. Right? Other axes will have different dependence, and you can see all of that from these measurements. And so you can map out the details of the magnetic field around a whole, and you can take different, put it between magnets, north and south, different configurations of magnets, and you can see how these fields actually work. So it's a beautiful thing. Okay, pressure sensors. So get your, choose the pressure sensor on your phone, okay? The pressure sensor on your phone is based on this like thin membrane. It's got a thin film, a silicon resistor on it. When the membrane basically flexes, it changes that resistance. That resistance is converted into a pressure, okay? So the question is, you know, what would happen if you measured the pressure like above your head and below your head? So try this experiment. So start measuring the pressure, set your phone on the floor, measure the pressure, okay, start it up, measure it. Oh, you gotta put mine on.
Pressure, 2 meters, pretty good pressure. Are you guys getting the difference?
You got what
Gotta wait 30 seconds. 30 seconds. I think you guys did. I think you guys a little fast there.
Then, yeah, you gotta wait for it.
It reaches a plateau. I'm gonna go up.
I'll step on my phone.
I'm not gonna step on your phone, John.
What do you guys see? Does anybody see a difference?
The thing is, less pressure as it goes up.
There's more pressure,
No, less pressure.
less pressure. Who would have ever thought you could measure that small change in pressure with your phone? Did you ever think that pressure was that substantial?
I mean, you don't have to move it much at all.
No.
Now it goes like this here.
Yeah.
Here, and it goes. Looks like that. And then no pressure.
So anyway, so this is
What about putting the phone inside a bed type vacuum in water?
Yeah, so I've done that, and I've measured the density of water that way.
Yeah.
Dave, you have a
I have
question?
water in my phone. I think it's water.
Or a flute.
Yeah.
Like this. Oh, God. It's okay. I'm just a little bit water.
But the other thing you could do is you could prove that in an open container, even though it may, like an open, like a hot air balloon, the pressure is the same inside or out versus outside, it's open to the atmosphere. Because that's a big misconception students have, right?
Like a bowl.
Yeah.
Like a bowl of hot air.
Yeah, exactly. Oh.
Hey, Dave, we got a question real quick on the units on that. It says 8 Pascal. What are those?
Is that hecto?
Hectopascal.
Hectopascal, what, so what's that?
It's actually, I think,
Is that
it's like the thing that you pre-use, so it's like 100
100.
Pascal.
There we
100
go.
Pascal.
Yeah, and then there's decapascals, which are 10, so.
Anyway, you should have seen something like
Yeah,
that.
right, exactly.
So the other thing, so the next thing I did is, even when you're holding it steady, sometimes you see a little bit of change in pressure, okay?
I guess because you're.
And, well, you see a change in the signal. You don't actually know what it is, right? Is it noise? Is it drift? What is it, right? So this was kind of in my office, and I was measuring the pressure for a little while, okay? And I said, you know, what is that? So what would you do if you, how would you try to figure this out? What do you guys think? What would you?
Put it in different locations in the room. Record the same data, but at different locations in the room.
In different locations? And with that, what would that, how do you think that?
The most change would let you know where it comes from.
So what about you and your guy next to you, if you were both measuring pressure at the same time on your two different devices? What do you think that would tell you?
It would tell me,
If it was just noise, would you guys see something different?
no, if it's just noise, no, I don't think so.
Well, if it's just noise in your phone, his noise might be not correlated with yours, right?
Yes.
But what if it was real pressure changes? Would you see something, what would you see? If there was really pressure changes going on in the room?
That they would be the same. One of them would change faster than the other.
Or would they both change the same? Would you see that? Would you see both phones changing?
I don't know. I don't think so.
So I measured it with two different devices,
Okay.
and this is what I saw.
Yeah.
Is it sound? Is it sound waves?
So sound, so these are too slow to pick up sound. Okay, so this is a slower, device than a microphone, than the membrane on a speaker, or on a microphone, sorry.
Every 600 seconds.
Yes, sir.
I was about to say, difference could be like, maybe it's because like where one is able to hold, where one is able to like hold, it's like how say one can take the phone, how long could one hold hold a device, it's like
That's just a stable host.
yeah, and then like, how much someone's able to hold it, and like, that could change like why have different pressure,
So in this particular case,
I would think it-
yes, sir.
We did, you got 3 events.
Only three. One of them has more contacts.
Point is, all of them are 10 minutes, 600 seconds away.
But the one that has,
Strongly suggesting something artificial, like multiples of 10 things. So what is it, the ventilation in the room? The
So-
ventilation fan in the room, the thermostat?
So it turns out it was the elevator on my floor. I'm in a 5th-story building, okay? And whenever the elevator opened, and it opened the elevator shaft to equalize pressure between the floors, you saw it translate down the hallway to my office, which is like, 5 doors down from the elevator, and you could see it. But what you see is that these drifts and those fluctuations, they're all real. Right, so it can measure, it's measuring this thing very nicely. So one of the things that you guys probably learned in COVID, when we were doing like these vaccine trials, one of the things that's so important in experimental science is to run control groups, right? Understand how to use controls to make corrections for variables that you're interested in understanding, right? So if you're interested in, whether the safety of a vaccine, right? Okay, you can't just measure it on people who you've all given the vaccine to, right? You have to have some people who you're not giving the vaccine to, watch them simultaneously, and you have to subtract and understand the differences between the two, right? To be able to decide whether, the thing was actually having, any safety issues associated, right? Because you couldn't just say 5 people died in the vaccine study, because maybe 7 people died in this random, control group, right? So you got to do controls, right? So this is so important in science, so hard sometimes for us to figure out how to do and teach, right? Well, now you've got a way to teach it, right? Because here we have a control. We can have one phone sitting on the floor, and they can be measuring, the wind can be blowing, we can be doing all shutting doors, and the pressure in the whole room can be changing, okay? But I'm going to measure it. And now what I'm going to do is I'm interested in measuring the change in pressure as a function of elevation. So I change just that variable, that elevation variable on one of the phones. The other stays constant, and by looking at the difference, I can now determine the variable that I'm interested in, which is that pressure, the change in elevation. So here was a measurement I did when the wind was blowing strongly outside my house, okay? And if I just tried to measure the change in pressure from when it was low to when it was high, at these 2 different elevations, it's really hard to know where to draw that line. But I did a control experiment. And so I measured the pressure change that was taking place at the same time. I subtracted that from that control off, and now I get this beautiful, measurement that I can make of how the pressure changes with elevation. And this number allows me to calculate the density of air to 3 significant figures.
So you use the function to download this to an Excel spreadsheet?
Right, to an Excel spreadsheet, and then did the math. Just did the subtraction. Okay? So that's a pretty cool experiment. Okay. We're going to do one last thing before. Can we do one last thing before we break, or do you want to break now?
Yeah, no, you guys good? Oh, yeah.
Okay, because I don't want to, we want to have time for the breakout groups, and so we'll be quick on this. So go to audio scope, okay? And what the audio scope is doing is this is going to show you the pressure as a function of time, okay, measured by your speaker, right? So your sound waves are these mechanical waves. We always teach students, right? It's this modulation in kind of high pressure, low pressure, high pressure, low pressure from a vibration. So there's a vibration that's happening. It's producing these high and low pressures. That's propagating through space. Okay, and we can see that. We can pick that up. Yes, sir.
Do you need a microphone on the speaker?
Sorry, we pick it up on the microphone. Yes, sorry. Yes. So you're gonna sense it on the microphone. Okay. And so what I want you to do is I want you to whistle. Okay? And look at your singing.
I'm just gonna fake it.
Wow, that's good whistling.
If somebody's walking by, record us.
Yeah, but you should see my wife when I first learned this trick. You know, thinking I was absolutely nuts. So what you should have seen is this sine wave. Okay? And the reason you see that is because your whistle, turns out your mouth when you're whistling, there's a Helmholtz resonator, and it puts out a single frequency. And that single frequency, produces this very beautiful sine wave. So now when you're teaching about these mechanical waves of sound, right, your students can measure this themselves, and they can see this beautiful periodic fluctuation in pressure, and they can change the distance between peaks as they change the frequency of their whistle. Yes, sir.
I thought that the pressure thing was a little slow response.
No, that was with the pressure transducer for the barometer.
Oh, okay.
This is with the microphone, which is very high speed. Okay, so it's meant to pick up very high frequencies.
Can we figure out how efficient masks are with this?
Sorry?
We whistle with and without masks, figure out how efficient they are?
Well, what happens is your sound waves travel very effectively through things, but you can see how they might kind of muffle or change, or if they produce any kind of change in amplitude of the peak modulation. So that would be it's a great, interesting idea. Okay, so then the next thing on the iPhones. Download Spectrum View. On the Android apps, download Advanced Spectrum Analyzer Pro. Okay? So get one of those, download one of those other apps. So what this app is going to do for you is it's going to take that pressure wave that you just measured on audio scope, and it's going to do a Fourier transform on it and tell you what frequencies make up that particular wave, that mechanical wave.
The app already has that feature.
Pardon?
Dr. Ringwald had the Fourier transform open already.
Yeah.
Yeah, it's just that the one on this one works a lot nicer than the one on the Firefox. So the Firefox, you can do it on Firefox, it's just not as nice. This one produces better, these produce better, more usable graphs, and have more variables that you can change and stuff. So I want you guys to do this because this is pretty cool, and you're going to use this if you guys choose Professor Singleton's group. You'll get to use this in this group. Okay, so whistle into that one and see what you see. So get it started, whistle into that, and what you should see is a kind of a constant kind of a signal. If you choose the spectrograph, you'll see this, I don't know which one you guys have. If you have the Android, you'll see a different kind of graph. Okay? So So you'll see this, and if you go ahead and on the Android, you'll see something that looks like that. Okay? So that, and you can get this kind of graph also on the spectrum view if you choose the spectrum analyzer. Okay? But the next thing I want you to do is, now that you've seen that, sing into your phone. Okay?
I want
Sing
to
a note.
I'm gonna step away from Doug.
So I want you to sing a note, okay? Don't be embarrassed.
I want to hear you sing, John.
So instead of this nice single frequency, you're going to see this set of harmonics. Okay? And that's because your voice is a string oscillator, and you're going to see this whole series of oscillations due to the string oscillator.
I think that one's for iPhones.
And you can have the students,
Yeah.
you know, see where what the fundamental is. So this is the fundamental frequency right here, the string oscillator. Then you see all of these that come up. If you analyze them, you'd see that they're all, you know, F of n equals, you know, the n times the first frequency. So these are all multiples of the initial frequency of the fundamental. And so you can study all these kinds of
that's what that is.
Okay? So there's a ton of stuff we can do. Okay? There's all these other sensors. There's so many apps with the things I showed you, the experiments you can do. On my website, in the lab, there's like 2,500 pages of experiments that you can look at that I've developed over the last 2 years. And you can go there and explore if you want. We're going to explore a couple of them now. Okay, so we have 5 different groups that are going to do different experiments. Okay, and so you guys can choose which of these things you want to try, and you'll have one of your coworkers or faculty leading you in that experiment. Okay?
So I'm doing the coin resonances, and I'm going to do it up here. Dan,
Yo.
stand around.
Yo.
Where's you?
I'm on a table right outside that other door. Yeah.
And Dan is doing magnetic storage, and then Pete, where you? So all right, where are you? You're on.
Set up, yeah.
Oh, what? So are you set out at one of the tables outside?
I haven't looked.
Okay, so you're at the table in the back there. Okay. So and then let me see. Chance, you're outside. So Chance is doing investigation of flat panel displays, and then